So here we've got the same animation as last time. We've got our three particles being subjected to a harmonic oscillator potential and a damping force, while the white particle is experiencing a driving force. The only thing I've added is these little wedges. These indicate when two particles are bonded. So right now, white and green are bonded. Now white and red are bonded. And then for a second there, they were all bonded. And this is just kind of randomly turning on and off. I haven't actually implemented any bonding forces yet. This is strictly a visual. I didn't want to have to go through all the visual creation and debugging on camera, so I made that off camera. This is to mimic here in figure 1A of the paper we've been looking at, these little arcs that indicate bonds, or over here in these network diagrams, the connectors between the particles. So that's, for right now, that's what a bond is going to look like in our code. I wanted to take just a couple minutes at the beginning here and show you how I set that up, and then I want to actually add in the physical bond between the particles to see how the animation changes. So to create that visual, I've used the curve function in VPython. Curve takes in a number of, really any number of points, and then connects each of those with a line segment between the neighbors. So it starts at particle 1's position, it goes to the other particle's position, and in the middle, we just put in a point directly in between the two. So its x component is the average of the two, and then its y component is just one above. Since we're only moving in the x direction, we're not we're going to have the bonds kind of arc up into the y direction. Again, just like figure 1A back here in the paper. So theirs are nice and smoothed out. I haven't yet made it fancy enough to be a curve. Right now mine are wedges, but it's basically recreating this diagram here. And so what we have to do is every frame we have to update those positions. So here I've put in a loop over all the particles. And so whenever we loop over the particles, we're going to update the points of those. I'm calling them arcs here because I was originally using the arc function, and then I had trouble figuring out how to get that to work. So we're just using line segments here with the little wedges, so I suppose I could change them to wedges. But what I'd ultimately like is to be able to make them an arc. So I'm going to keep the name there in hopes that I'll figure out how to use the arc function in a future video. Basically, you modify the points. You modify the 0th point, the 1st point, the 2nd point. And again, it's just the starting particle, the ending particle, and then a wedge point in between the two and slightly up. So in order to do that, we have to loop over the particles twice. So we're calling the first one I particle and the second one J particle. Now this is where you have to be careful with a double loop like this, because we don't want to double count particles. So for example, we don't want to loop over particle 0 and then particle 1, and then loop over particle 1 and then particle 0 and particle 0, because then you're double counting. And in fact, up here I've only got 3 curves. So the way to think about this is that you're only counting it when I particle is less than J particle. So the way you can avoid that double counting and avoid having an arc going from particle 0 to particle 0 is to start your second loop at I particle plus 1. So in other words, I particle is going to run, in this case, from 0 to 2, but J particle is going to run from the next one in the list up to the maximum. So when I particle is at 0, this thing goes 1 to 2. When I particle is at 1, this thing only goes to 2. When I particle is at 2, this thing doesn't loop at all. So I could technically make this length particle list minus 1, but you know, it's going to skip over the whole thing, so it doesn't really matter if it has one extra little loop doing nothing. And so we've got the updates here. So this is updating based on the positions, because we are updating the positions of the particles. And here is where we're going to determine whether the bond's state changes, meaning whether we're going to turn the bond on or off. So what we do is we pick a random number. We're using this random number generator. And here I'm just using a uniform constant, I'm using a constant probability of 1%. So 1% of the time, so 1 out of every 100 frames, a bond will flip. So what we do there is we just say we're going to flip the entry in the bonding matrix, which we haven't talked about yet because we are not quite using it yet. But here what we're doing is we're turning the arcs from visible to invisible or vice versa. So if it's currently visible, it will become not visible, meaning invisible. If it's invisible, it will become not invisible, meaning visible, and so on and so on. So using this not operator nice and compactly flips a true to a false and a false to a true. And then I think that's it. The rest hasn't changed. I've added in some comments for what I need to do later. This bonds matrix here, this is what's keeping track of which particles have formed a bond. So basically a 0 indicates no bond. So 0 equals no bond. And 1 is a bond. I suppose in principle it's possible to make this a non-integer value, to make it a floating value from 0 to 1 to indicate maybe the strength of the bond. But I think for right now we'll just stick with it as a switch. So 0 means no bond and 1 means a bond. And so what we're doing here is in line 64 and 65 is flipping those zeros into ones and ones into zeros. And there's a neat little trick for doing that. If you just take 1 minus a 0 or a 1, it turns it into the other one. So if this bond is currently 0, 1 minus 0 gives you 1. So you switch from a 0 to a 1. If the bond is currently 1 and you take 1 minus 1, the whole thing becomes 0. So you go from a 1 to a 0. So this is a nifty little switching formula between ones and zeros. It avoids having to set up some if then else blocks and things like that. It's just nice, compact, and in one line. And like I said, right now this is not doing anything because we haven't put in the force of the bond. So I think now is going to be our time to do that. So that's going to come here under the forces on the particles. So what we need to do is we need to loop over the particles. So I'm going to copy this line here. Oops. I'm going to need to loop over the particles twice, just like we did before. Well, not just like we did before. Let's take a look at how this is going to be different. Oh, that's weird. That didn't... okay, I must have grabbed it at the wrong indentation or something. Let's see. That's indented properly. That's indented properly. Okay. Except now we do want to loop over all of them because we need to... We do need to double count this time because we need to have the force of 0 on 1 and the force of 1 on 0. So we're going to have this thing start out at 0. And let's see. What I want to do next is add the interparticle force based on the bonding matrix. So what I need to do next is, let's see, what am I calling the force? We're calling it particle list of iParticle net force. Cool. Oh, actually, excuse me, I'm already looping over iParticle, so I don't need to do that again. That's going to be problematic. So let's see here. Let's put that out there, put that out there. There we go. All right, so what we're going to do is we're going to add to this thing. So I need to add to it. So I need the original plus I need my k value. Let's call this k underscore bond times the distance between them. Let's see. Actually, this needs to be a negative sign because a spring force is negative kx. So let's think about this. This needs to be going from the current particle to the new particle, from the I to the j. So I need to start out with j's position. So let's see here. So I need to have particle underscore list of j underscore particle. So I'm accessing the j particle dot its position dot x, since we're only working in the x direction. Actually, no, this thing needs to be a vector because the force is a vector. I'm not making that mistake a third time, at least not today. Let's see, so then I take minus the same thing for the I component, for the I particle, excuse me. I particle, close that up. All right, now I need to double check this, make sure that I have put this in the correct order. So let's suppose that I particle is located at x equals 0 and j particle is located at x equals 5. Okay, so that would be 5 minus 0 would give me a negative force, and so that would pull I to the left. So I actually have this wrong. I need to make this I particle minus j particle, right? Because if I have, okay, let's run that same scenario again, let's suppose I is at 0 and J is at 5. So 0 minus 5 gives me a negative. So I have a negative 5 in the parentheses here. That's being multiplied by a negative out here. So I have a positive 5. So it's going to pull particle I to the right. And that is the way I want it to go. Good. Good. Except that this is only activated if I have a bond between the two. So I need to access this bonds argument here, this bonds matrix copy. It's not really a matrix, it's a list of lists, but that makes it function like a matrix. We're going to take this, multiply it by this thing. So again, this is 1 if there is a bond, and it's 0 if there's not a bond. Right? Okay. Yeah, so this is going to tell me this. And it doesn't really matter whether I have this one as I particle, J particle, or J particle, I particle, because I'm going to keep this matrix symmetric thanks to this little line of code right here. So I'm only changing IJ up here, but then I'm making JI equal to IJ. So JI is always going to be equal to IJ. It's going to be a nice symmetric matrix. Okay, so we have added in the interparticle forces. We're doing for J particle in range 0 to length particle list. We're already looping over the I particle. And I think that means we're good. So we have this negative K0 here. So we have the spring force. Then we're adding on the damping force. If it's particle 0, we're adding on a driving force. And here we're adding on the each of the interparticle bonds, which are being turned on and off elsewhere. So I believe that means we're good to go. Oops, K-bond is not defined. Right. I had a mental note to do that, and forgot to do that here. Let's put that under the bond properties down here. Let's say K underscore bond. Now let's see, my current well has a stiffness of 1. Let's make this a little bit weaker than the well, so let's say 0.5. All right, once again. And there we go. So we should see these things behaving notably differently. Yeah, that just stretched out way farther. In fact, one of the things we'll see is that white is the only one being driven by the external force, but it's now, because of these bonds, transferring some of that energy to red and green. So we shouldn't see red and green slow down like they did before, and in fact, we're not. So what we're seeing here, this is cool, we're seeing an external energy being pumped into the white particle, and that's now interacting with the red and the green. In fact, white is not behaving the same as it was before because it's got those other forces. Yeah, oh, see there? It's lingering there in the middle now. Because what that also means is that the white one is losing some energy to these, and then they're losing energy to the surroundings from the damping force. So this is pretty cool. We've got our bonds set up. Let's try an extreme case. Actually, they're settling out right now. Let's try an extreme case. Let's suppose we made it to where they were always bonded. Actually, let's do the other extreme case first. Let's make it to where they are never bonded. So this number here represents the probability that that they'll bond or break a bond. Let's make that 0. This should give us the same results as before, to where they are never bonded. Oh, except I never turned off the animation there. Okay, so ignore the white bond animations up here, kind of like you did before. Yeah, these are behaving the same. That's cool. All right, cool. And now let's make it 100% probability that they will form a bond. In other words, these things are always going to be bonded with each other. So let's run this. And I think I actually just, in my head, figured out a problem. Oh no, 100%. No, that doesn't mean they're always bonded. It means they're always flipping between being bonded and unbonded. Oops. My bad. All right, so in order to do that, let me think about this. Oh, I would have to make these all ones, wouldn't I? 1, 1, 1, 1, 1, 1. So this is going to be always bonded. And actually what I need to do, if I have them start out unbonded, I just realized I need to have these arcs start out as invisible. So I actually have the reverse happening right now in my animation. I hadn't thought about that before. Let's take a look at this. So here they are always bonded. Yeah, that's definitely a different behavior than we had before. In fact, because I know this video is running a little longer than the last several have been, let's up the rate by a factor of 5. There we go. Oh, that is cool. That's really neat. So the white one's being driven. These two are reacting to it because of their bond. And they'll just keep going back and forth like that. That's kind of cool. Awesome. Okay, so let's do this. Let's have them start out unbonded. Because I think it makes sense to have them start out as unbonded. It doesn't ultimately matter. I guess I don't know in the paper whether they started out as unbonded. But what we're going to do is we're going to make these things invisible. Let's see. Let's do for arc in arcs. Arc.visible equals false. There we go. That should make it so that these things are always invisible. So that they start out invisible, excuse me. And with my 0% probability, they should start out. No, they're starting out visible. Arc.visible. Oh, right. These are what I'm accessing there is the list. So I need a for list in arcs. For a list in arcs. Now I need for arc in a list. Now make that arc.visible equals false. Okay. Because it doesn't do anything to make a list invisible. Because they're already invisible. They're hidden inside the computer. Cannot create property visible on numbers. Oh, right. So this is storing as a number. So this is turning out to be more difficult than I thought. Can I simply do comma visible equals false? Control 2. Property pause must be a vector. Oh, right. Okay, so let's do this then. Let's say position equals that. Will that work? There we go. Okay, that's what I need to do. I need to make this list a list of positions and then set up visible equals false. Down here, visible equals false. I need a comma. And I need to make this position equal. So I just learned how to use curve yesterday. So this is a learning experience for me too. Okay, so these should all now be invisible and deactivated. So the bonds are deactivated. The visualization is deactivated. Cool, and that's what we had before. Awesome. So now, okay, now let's give it the real test. Let's make this 1% probability of switching between having a bond and not having a bond. And there we go. So now they only have the connector when they are bonded, and it's invisible when they are not bonded. Okay, so this is a nice, fun little sample model. What we need to do next on the next video to make this more physical is we need to change how this probability is determined. Currently it's a flat 1% probability. We need to bring in what's called the Arrhenius model. I will look up the pronunciation of that before the next video, and we're going to turn this into a function of the energy or the distance between the two particles. So thank you so much for watching. I will see you next time. Bye-bye.